Here's the reaction for a lead storage battery. Solid lead plus lead dioxide gives lead sulfate. Our goal is to balance this redox reaction in acidic solution. For a lead storage battery, you're dealing with sulfuric acid. In a previous video, I've already gone over how to balance a redox reaction in acidic solution. So this video is just a review of that one using the lead storage battery as an example. The first thing we need to do is assign oxidation states, and we'll start with solid lead. The oxidation state of an element is 0, so it's 0 for solid lead. We move on to lead dioxide. For oxygen, the oxidation state is -2, and we have 2 of them, giving us -4 for the total. The sum of the oxidation states in a neutral compound is 0, so it must be +4 for lead. We move on to lead sulfate. We know that sulfate is SO4 2-. Therefore, we're dealing with lead 2+, the lead 2+ cation. So the oxidation state is +2. Next, we write our oxidation half reaction. So what is being oxidized here? Solid lead is going from an oxidation state of 0 to an oxidation state of +2. That's an increase in the oxidation state. So that's oxidation. So we write down here solid lead is going to lead 2+ ion for our oxidation. We have sulfate present, so we need to have sulfate on both sides. So if we have solid lead plus SO4 2-, that goes to lead sulfate, PbSO4. Next, we look at our atoms, and we have 1 lead on the left and 1 lead on the right, 1 sulfur on the left, 1 sulfur on the right, 4 oxygens on the left, and 4 oxygens on the right. So all of our atoms are balanced. We move on to balancing the charge. You balance charge by adding electrons. So let's figure out how many electrons we need to add and where do we add them. On the left side, we have 2 negative charges. On the right side, our overall charge is 0. So we need to make those charges equal. And we can do that by adding 2 electrons to the right side. So now the charges are balanced. Remember, oxidation is loss of electrons. So this is the half reaction that occurs at the anode of our battery. Next, we want to do the reduction half reaction. So we need to write down our reduction half reaction. We can see that we're going from +4 to +2. That's a decrease in the oxidation state. So for our reduction half reaction, it would be PbO2 going to Pb2+. Once again, we need to add in our sulfate since that is present. So on the left side, we would have PbO2 plus SO4 2-, and then going to PbSO4 on the right. Next, we need to balance our atoms. So we'll start with lead, 1 lead on the left, 1 lead on the right. And once that's done, right, and the sulfur is balanced too, 1 sulfur on the left, 1 sulfur on the right, we look at oxygen. So let's look at the left side here. So we have 2 oxygens here and 4 here for a total of 6 oxygens. So 6 oxygens on the left. And on the right we have 4 oxygens. So 4 oxygens on the right. You balance oxygen by adding water. So we need 2 oxygens on the right side. So we can get that by adding 2 waters. So if we add 2 waters, now we have the proper number of oxygens. We just added 2 more oxygens to the right side. Next, we balance hydrogens by adding H+. So let's look at the right side. We have 4 hydrogens on the right. And on the left, we have 0. We have 0 hydrogens. So we need to add 4 protons to the left side of our half reaction. So if we add 4 protons to the left side, now hydrogen balances. So we have 4 on both sides. Next, we balance charge. So what's the overall charge on the left side? We have 4 positive charges here and 2 negative charges. So we have a total of 2+ on the left side. On the right side, it would be 0. So we need to add 2 electrons to the left side. If we add 2 electrons to the left side, we get our charges balanced. So now we have our reduction half reaction. Our reduction half reaction occurs at the cathode of our battery. So let's add our two half reactions together. And we can do this because we have the same number of electrons. So let me box this half reaction. So for our oxidation half reaction, we lost 2 electrons. And for our reduction half reaction, we gained 2 electrons. So those electrons cancel out. So we're going to add our two half reactions together to get the overall reaction for a lead storage battery. So let's add all of our reactants. Let's start with these up here. So we're going to have solid lead and sulfate. So let's start by writing that. So we have Pb plus SO4 2 minus. And then for our reactants down here, we have 4H plus PbO2 plus SO4 2 minus. So we have 4H plus PbO2 plus SO4 2 minus. For the products, we have PbSO4, right? So we have PbSO4, and then down here we have PbSO4 and 2H2O. So PbSO4 plus 2H2O. We've already canceled out the electrons, so we don't need to worry about that. Let's simplify this. All right, so how can we simplify this? On the left side, we have lead, so Pb plus PbO2, so Pb plus PbO2. Then we have 4H plus, so 4H plus. Then we have 2 sulfates. We have 2 sulfates here, so we'll write 2SO4 2 minus. And then for the products, we have 2 PbSO4s. So that would be 2 PbSO4 plus, that's a 4 here, plus 2H2O. All right, so we've finally done it. This is our overall reaction for a lead storage battery. And sometimes you might see this written a little bit different in a textbook. You might see two of these protons added on to these 2 sulfates to give you 2HSO4 minus, leaving 2 protons left over, so 2H plus. So that's just another way to write what's happening here. So this is a voltaic cell, right? You get a voltage out of this spontaneous redox reaction. And one of these cells has about positive 2 volts. So the cell potential is about positive 2 volts. So if you take 6 of these cells and add them together, you get a car battery. And a car battery has a total of 12 volts. So 6 cells, each one with 2 volts. When the car battery discharges, right, the spontaneous redox reaction delivers a current and your car engine starts. Once your car is running, the reaction is reversed, and that allows you to recharge your lead storage battery. The reverse reaction is ready to go because your lead sulfate here is a solid. So if we go back and we look at our half reactions, for our half reactions here, we have lead sulfate for both of them, and it's a solid that precipitates on your electrodes. And so therefore, the reverse reaction is ready to go, and you can recharge your battery. So first you could think about this as a voltaic cell, right, which produces a current using a spontaneous redox reaction. And then you could think about an electrolytic cell. A current is used to recharge your battery. A current is used to drive a non-spontaneous reaction. And so a lead storage battery is rechargeable, and that makes it very useful in car batteries. They last an extremely long time.